Okay, so it's my great pleasure to introduce Ralf Rothenberger from the Hasso-Plattner Institute at the University of Potsdam in Germany. I had the pleasure of visiting him actually with him and his advisor at HPA, which is a very nice place. Ralf is a PhD student over there, and he works in complexity theory in general, but he's particularly interested in why SAT solvers are so efficient. So without further ado, Ralf.
Yeah, thanks, Vijay. So I'm going to tell you something about two structural parameters that in part already came up, which are heterogeneity and locality, or as we interpreted, geometry. And I'm going to present you essentially our latest result from SODA this year. And yeah, I think I don't have to motivate that we have a lot of structure in industrial set instances. What you can see here are the primal graphs of, on the left, a random k-set instance, and on the right, a hardware model checking instance. This is, on the right, is the instance that also Jordi mentioned to show that it has a power law distribution. And what you can see here in this graphical representation is that it also seems to have a nice community structure with the communities colored in different colors here. So Stefan and Jordi already mentioned a lot of parameters. For example, heterogeneity, locality, low fractal dimension, and others. But the ones we are interested in, as I said, heterogeneity and locality. And I'm going to start by talking a bit about heterogeneity. And we are going to interpret it as Jordi did. So we're going to assume that industrial instances seem to have some scale-free structure or some kind of power law distribution. So if you have a random k-set instance without this structure, the distribution of variable frequencies, so how many variables appear a certain number of times, looks something like this, like a Poisson distribution. But in industrial instances, it looks something like this. Especially, it has these very long tails, and it seems to resemble a power law distribution. That means the fraction of variables that appear I times is proportional to I to the minus beta, where beta is the power law exponent, and this is just some constant that is intrinsic to the instance you're looking at. So Jordi also presented their model for generating instances with such distributions. And well, essentially you choose m clauses at random, and for each clause you draw k variables without repetition. But now you don't draw them uniformly at random, but with a probability proportional to a power law probability distribution. And you can see below how to do this in a discrete way. So the ith Boolean variable essentially has a probability proportional to n over I to the 1 over beta minus 1, where beta is, again, the power law exponent. And then you negate the k variables with probability 1/2 to get a random clause. And we studied this model extensively over the last years, and we got some results regarding the satisfiability threshold that I, in part, already talked about last week at the Fellows talk. So today I'm going to concentrate on something else, namely on the resolution width and resolution size of those instances. And we showed in our recent paper, using the framework of Ben Sasson and Richardson, how large the resolution width of these instances is. So these are lower bounds for the exponent c of the resolution width, n to the c, depending on the power law exponent beta. So for very small betas, for example, if you have k equals 3 and your beta is smaller than 2.5, we know that the resolution width is actually constant. And above that, it slowly increases up to being linear width. And something similar seems to hold for all constant values of k, where the resolution width slowly increases and then becomes linear. So we have this intricate dependence on the power law exponent that's very interesting, that we also like to study with regards to satisfiability thresholds. And as you might also know, from the same paper of Ben Sasson and Richardson, a resolution width of W implies a resolution size exponential in omega W squared over N.
There's a question, Ralf,
There's a question,
by
yeah.
Noah. So it says, are these lower bounds or are there matching upper bounds?
They
So the
are lower
graph,
bounds. Those are all lower bounds. So it could be that resolution width already is linear earlier than what I showed you, because we also have this jump here where resolution width suddenly becomes linear. And this is due to the formula suddenly having high bipartite expansion, which is essentially what you use in the work of Van Sussen and Richardson. But you can also show something if you don't have high bipartite expansion, and this is why we also have results below that point.
This is a proof or this is empirically observed?
This is a proof.
Okay.
Yeah, those are all rigorous results. So as resolution width and resolution size are somewhat related. And what you need to have non-trivial lower bounds also on the resolution size is that your width is at least square root n. And well, you can essentially read that off from the chart I show you, but I save you the trouble and I'm going to present it a bit more graphically. So these are essentially our results on satisfiability and unsatisfiability, depending on power law exponent and the closed variable ratio. And now we can complete this picture a bit by also having results on the resolution size. We have that if the power law exponent is large enough, above 2k minus 2 over k minus 2, we have exponential resolution size. Above 7k minus 2 over 3k minus 2, we have at least super polynomial resolution size. And below 2k minus 1 over k minus 1, we have constant resolution size. So there seems to be a transition going on where resolution size increases with the power law exponent. And in that area in between, we still don't know what happens. It could be that there's some kind of sweet spot where resolution size might be polynomial, but I personally doubt that. And to have also some values that you can maybe interpret more, I give you a little table of where these bounds are for different values of k. And what's important here is, well, below this first column and the second column, there's the gap of where we don't know what happens. And this is usually not a large range of power law exponents where we don't know anything. So this is something for future work, maybe closing this gap. And yeah, so those are essentially our results on heterogeneity. And but we also wanted to look at locality. And usually when you look at locality, you have some kind of measure for that. For example, modularity, which essentially says that if you have 3 vertices and 2 of them are connected to the third one, then it's more probable that these 2 vertices are also connected with each other. And we already have, or there already are some results on modularity and effect on set instances. So modularity alone doesn't seem to be a good measure, because it still may result in bad solver runtimes, and it may also result in exponential resolution size. So instead of looking at locality as modularity, we have a different interpretation, because we assume that we have some underlying geometry in where our variables and clauses live in, and locality comes from connecting clauses to variables that are somewhat close in this geometry. So we don't need to have any modularity. We immediately get some measure of locality by assuming an underlying geometry. More precisely, we consider a model with the following parameters. Again, we have n variables, m clauses, and we also assume the width of the clauses to be k. But we can also assume some variable weights, again, for example, power law weights, and we assume that our variables and clauses have positions in some geometric space, for example, a d-dimensional torus.
So Ralf, there is a question with
Yes.
regard to your previous results that you presented. Are the width lower bounds using expansion? Did you use the expansion formula?
Yeah, I know. So we have two kinds of lower bounds. One of them use bipartite expansion, as the result by Ben Sasson and Richardson does. The other one doesn't use expansion, but essentially the properties from the Ben Sasson Richardson framework that you need to show high resolution width that are usually implied by expansion. So you don't have to have expansion, but you only have to have those properties, and you can show them directly without having high expansion. So yeah, we use expansion, but we don't only use expansion. We can also show something if we don't have high expansion. Okay, so we assume to have this geometric model. What we do is we randomly distribute our variable nodes in our geometry. Then we randomly distribute our clause nodes in our geometry. And now we want to connect each clause to k variables. And to do so, we have to consider two things. First of all, the weight of the variable, and second of all, its distance to the clause node. So to have a measure of distances, we assume p norm with some p, which can be any natural number or infinity. And we also assume to have some temperature, which controls how many long-range edges or how many random edges you can have. So if the temperature is high, a clause doesn't necessarily connect to the variable with smallest distance or the variables with smallest distances, but it might also connect to a random variable which might be very far away. And the probability to connect a clause to a variable or to draw a variable is proportional to the expression I give you down there. So as you see, it depends on the weight of the variable and the distance between variable and clause. And it also depends on the temperature. If the temperature is very low, the clause draws the k variables that are closest regarding the weighted distance. So the weight still plays a role there. And if the temperature is very high, it essentially only draws random variables, so you get something like the uniform model. So this is the model we consider. And what do we show? Right. I forgot. Each clause connects with 3 variables in this example. And we show essentially that if the number of clauses is linear in the number of variables, then in this model, asymptotically, almost surely there's a very short unsatisfiable subformula, which essentially only consists of k different variables. And this also holds if the weights of the variables are heterogeneous. So if we have these conditions, which essentially say the maximum weight shouldn't be too high, and the sum of the weights should be linear in the number of variables. So this could also mean that you have a power law distribution. This satisfies these conditions. And we can also have a moderate influence of random edges. So the temperature can be anything between 0 and 1. And well, then we know our formulas are very trivially unsatisfiable for constant clause variable ratios. How do we show this result? Well, the idea is pretty easy. Imagine again that we have our geometry and we randomly distribute our variable nodes. What we look at are Voronoi diagrams of the nodes in this geometry. So the Voronoi diagram of this would look something like that. So for each node, you have a region, and that region essentially says if a point falls into that region, it is closer to this node than to any other node. For example, all the points here in this region on the left are closer to this variable than to any other variable. If you would now randomly also distribute your clause nodes, then by looking at the region the clause falls into, you can immediately say which variable it is closest to. If those clauses would only contain one variable, then you would immediately know which one variable it would contain just by looking at the region it falls into. And you can generalize this idea of Voronoi diagrams also to look at more than only one variable. And this is called an order k Voronoi diagram. So order k Voronoi diagrams, you have also regions, but not for every variable node, but for every subset of k different variables. And you can draw a diagram in a similar way. And then if you randomly draw your clauses, just by looking at the region the clause falls into, you know exactly which k variables this clause contains. And
there's a question. There are two questions. I think one by Nicola, but we can take it after the end of your talk. The other one is relevant to your current set of slides. The question is from Sybil. It says, did I understand well that the clauses and variables on slide 12 are distributed randomly? Where is the connection to the true structure of the formula?
Which structure?
I think Sybil is trying to say what, actually, I don't know. What do you mean by true structure, Sybil? Yeah, let's take it at the end of the talk, Sybil. Okay.
Okay.
Yeah.
No,
there you are.
Sorry.
Okay, go ahead.
No, because it depends on how you distribute your points. No.
Yeah, I mean, sure it does. But we assume that they are distributed uniformly at random.
Okay.
Yeah. So in order to not have any edge cases, we also assume that our geometry is a torus. Yeah. So this is essential. But you can model a lot by having the right geometry and norm already. Yeah.
So when you have an industrial instance, this should have some quite some defined structure, or I don't know how to. Maybe my question was too unclear.
So essentially what we're capturing with this model is locality. So if you use this model, you get some kind of community structure or locality for free. However, it's not clear how industrial instances actually relate to that model, because you would have to show that you can somehow embed the incidence graphs of industrial instances into a suitable geometry, which you also have to find first.
Yeah, okay. Yeah.
But maybe that's possible, we don't know. And as I said, there's a lot of geometries that are captured by this model. For example, you can also think of having a hyperbolic plane, which gives very good results, at least for complex networks. And so our hope was that maybe something similar holds for industrial set instances.
Okay, yes, thank you. Wrong question. You can study what happens if we have a certain structure, but yeah, of course. Thank you.
Yeah. Okay, so the idea is now to look at the order K Voronoi diagrams and the regions the clauses fall into. And our hope is that the number of possible regions is not too large. So if the number is somewhat big O of n, we can essentially use a simple balls into bins argument, because we randomly distribute m clauses, which is linear in the number of variables, into O of n bins, which are our regions. And the result by Ralf and Steger tells us that we get a bin with a maximum load of omega log n over log n with probability tending to 1. So this would mean we would have log n over log n many clauses containing the same k variables. And in our model, we choose the signs of variables in those clauses uniformly at random. So this would mean we have a high probability of having an unsatisfiable subformula. So how big is the number of regions in our geometry? Well, we can actually show, and we show in our paper, that in some cases, for example, for order 3 Voronoi diagrams in two-dimensional Euclidean space, the number of regions can be larger than n squared, which is way too large to apply the balls into bins argument. However, the thing is we don't have a worst case, so we randomly distribute our variables uniformly at random, and we can use this fact to show that in expectation the number of regions is small enough. So this has already been shown before for high dimensions, for high orders, for weights, and for any p norm, but to the best of our knowledge, not for all of these things together, which is what we can assume now. And this is already enough to use the balls into bins argument and to show that our formulas are, with probability tending to 1, unsatisfiable. So this captures a lot of cases. It captures, well, we can choose arbitrary constant k. We can choose our weights with the constraints that I showed you before, for example, power law weights. We can show any p norm. However, one thing is still missing here, because what about temperature? What if we allow random edges to some extent? Well, if we have high temperature, this could easily destroy our proof idea, because even if a clause lands in a certain region, it does not necessarily contain the k variables from that region. It might contain a variable that's very far apart. But for temperature smaller than 1, we can actually show that there's a constant fraction of clauses that behaves well. So if the clause lands in a region, it contains exactly k variables from that region and no variable that's further away. And then our argument with balls in the bins still goes through. So this is essentially the idea of the proof. And this was our take on geometry or locality via geometry. And well, I'm going to conclude now and recap what we saw. So essentially, what we showed was that heterogeneity, in terms of a power law distribution at least, doesn't seem to help much. So if the power law exponent is too small, you get a constant resolution size. If it's too large, you get super polynomial resolution size. Although it might still be that there's some sweet spot in between there, which might model CDCL runtime on industrial instances nicely, but I actually doubt it. And if you have geometry, it seems to help too much. So it makes formulas trivially unsatisfiable if you draw a number of clauses that's linear and a number of variables. And this also holds if you have heterogeneous variable distributions, like a power law distribution. If you have some moderately many long edges or random edges, and it holds for many different geometries. So for d-dimensional tori, for d-dimensional hypercubes, and also for hyperbolic planes. Yeah, so this was our take on heterogeneity and geometry. Well,
thank you, Ralf. Thank you for a great talk. I'll go back to Nicola's question.
Yeah, please.
It says, are you using expansion for the exponential lower bounds region and the other properties for the super polynomial lower bound region? So you mentioned some other properties other than expansion that you used to prove lower bounds, right? And is it the case that the other, first of all, what are those other properties? Secondly, are you exclusively using them for the super polynomial lower bounds?
Essentially, yes. So yeah, we're using these other properties for super polynomial lower bounds, and those properties come from the paper of Ben Sasson and Richardson. And essentially, what you need are two properties that you don't have, so that any proof needs many clauses from your clause base to any unsatisfiability proof needs many clauses from a clause base to be derived, which essentially translate to you must have a large unsatisfiable subformula. You can't have a small unsatisfiable subformula. And the other property is that you have many in each subset of clauses, you have many unique variables, which then translates to large resolution width in the proof you derive.
Thank you.
Yeah.
Jody, I think, had a comment. It says, let me read the comment. All these models of generations of random formulas are simple ways of generating random formulas with properties observed in most industrial instances. It does not mean that they're perfect.
It's an answer, in fact.
Sorry?
It was an answer to the previous question, not a question itself.
No, I know. It's a comment. Yeah, but I think I agree with the heterogeneity point. In other words, the heterogeneity property that you're exploring is indeed also observed in industrial instances. But I'm not sure so much about the way you're defining geometry or the way you're defining locality via geometry, because there it seems like it's an overkill because you are embedding these 2 to the k unsat formulas, which are trivially unsat, right? So therefore, I think that while it's interesting result, I feel that the geometry is probably too strong, and it has to be somehow weakened in order to reflect reality.
Yeah, I mean, essentially, this is what we wanted to show. Geometry is too strong because you could, I mean, we want to capture locality somehow, and there are many ways to do that. And one of them is geometry, and we wanted to show, no, don't use geometry, that's too much.
Yeah, and the problem with modularity, as you said at the beginning, is that you can show the existence of formulas that have good modularity but have very large proofs, which was done by Nathan Mull and company. So that's the problem. Modularity is too weak on its own.
Yeah.
So we have to somehow strengthen that. But I agree with the overall point you raise here, which is heterogeneity and locality seem to be two structural parameters which have the, if properly defined, would likely have both properties that was mentioned by Stefan, that they satisfy the correlation model and they are also rigorously analyzable, which was what initially was stated by in Stefan's first slide, that ideally you would like both of them, but it turns out that the parameters explored so far are either in one box or the other, but not both as yet.
Yeah.
Thank you again, Ralf, for a great talk.